All right. We're going to start optimization notes. So just want to give you a heads up that the test is going to be on Friday. Um, the derivative graphs, I know a lot of students weren't here on Friday. So I will go over this again, but I really would encourage you to watch the video, see if you can understand that process. We are going to have one curve sketching problem, one derivative graph sketch problem, and one optimization. Those are the three new extended problems that you'll see on your test, and the rest of the test will just be problems that are similar to what you saw on the quiz. So the first derivative test for concavity, all that is going to be self-contained within one extended curve sketching problem. And so tomorrow, you'll you'll pick up the test review packet. I'm going to be at school tomorrow. I will have a help session in morning and afternoon, but I'm not going to be here in class. I'm going to be using this time to do some catch-up work. So Mr. Polo is going to come in and he's going to be going over the review with you. So I'm going to have him go over a full curve sketching problem, go through an optimization problem, and then maybe, yeah, I'll pick out a specific problem for him to go over with you from the packet. And then Wednesday, Thursday, we'll do a continuous test review. I will send out a list of days I'm available for help sessions. So it's going to be basically every morning and some afternoons. So so starting tomorrow morning, I will have a help session at 7:30, and then all the way till Friday morning. Okay, yes.
Are we gonna get our quizzes back before?
Yes, yeah. So working on about more than halfway through grading the quizzes. I'll give it back to you Wednesday. Wednesday. So you guys can see exactly what, if there's any trouble spots that we can clear those up before you guys take your test on Friday. Right, you'll get these calculators as well. Okay. Any questions? All right. Now, optimization feels a little intimidating, but I'm going to tell you exactly the type of problem you're going to see on the test, so you can just focus on working that type of problem. And so hopefully that'll kind of ease your mind, like, okay, if I know how to do this problem, then I'm good for the test. Hopefully you both. So, no. Okay. All right. So, optimization is the process of finding the greatest, either the maximum optimal solution or the least value of a function, the minimum optimal solution for some constraint, which must be true regardless of the solution. Optimization finds the most suitable value for a function within a given domain. So the big picture here is if I set the derivative equal to 0 and find and solve, that will give me basically what I'm looking for, my optimal solution. So once you get to this point, you're just looking for a critical point. That's an easy way of saying it. But when you find the critical point, you're also finding a place where the optimal solution exists. But then this is the easy part. If you can get down to your equation and find the derivative, then it's just power rule. And you've been doing that since unit 2, and even on the last quiz, you guys know how to find critical points. So, but the hard part is just setting things up. So we'll go through a couple of examples of that. So a manufacturer wants to design an open box having a square base and a surface area of 108 square inches.
divide this one by 6 because they're all identical size and divide by 4.
Well, we don't know if they're gonna be identical. Well, yeah, so basically yeah, that's the idea, that we're gonna try to force this, it's gonna end up trying to force it into as much of a cube as possible. Let's see how close we get to that. All right, so, we know that, so this is the key here. It says we want to find the maximum volume. So this is the equation that you're going to find the derivative for. Whenever you see the word optimal, maximum, minimum, and it doesn't matter if it's max or min, we're going to find the same way. We're going to find the derivative set equal to 0. It doesn't matter. There's not a different process for maximum and minimum. So we're going to create our volume equation, put a star next to it, because this is the equation that we're going to be finding the derivative for. Okay, now volume. How do we find the volume? Yeah, so here x, and h. Okay. They tell us that we have a square base, so we know that they have to share the same variable, but we don't know what the height is. So the height can just be a different variable. The volume is equal to x squared times h. Now surface area, if we think about what that really is saying, is we want to find the area of all the surfaces. So we know that the surface area is, it's an open box. So how many sides do we have that actually has material on it? Well, it's an open box. 5, right? So we have the base and you have 4 vertical sides, but then there's no covering up top. That makes sense. So there's five sides with material on it. Very good with that.
The only thing was within it.
No, we're building the box, so we're if you're talking about, if you have 6 sides of a cube, or if you have 6 sides of a box, they want to design an open box. So there's no material that's going to be needed for the top. So you have the base, and you have 4 vertical sides, so that's 5 sides. Okay, so what's the area of the base? X squared. Okay. What's the area of one of the vertical faces? Okay, using the variable that we see here. X times h. Yeah, sorry, this is h. Okay. So what about another vertical face, a vertical side? How many do we have of xh? 4. So I can combine like terms, right? X squared plus 4xh. Well, they give us something to work with. We know surface area is 108 square inches, so we can say 108 equals x squared plus 4xh. So the challenge here is, well, we know we want to find the derivative for volume, but we always want to get it down to one variable. But right now there's 2 variables here, but there's help, right? This is the supporting equation that's going to help us get this down to one variable so that we can find the derivative and find a critical point and find our answer. So which variable will be the easiest to replace out of this equation so we can get this down to one? Yeah, let's get the H2 replace. So if I want the H to be replaced, then I need to solve for H so I can plug in whatever H is equal to. So what can I do to solve for H? How would you rearrange this equation so we can solve for H?
H equals 108 divided by x.
Okay, you have the right idea, but we got to do this in the proper order. But you have the right idea. We do have to move things around to solve for H.
Sure.
Yeah, good. We're going to subtract the x squared first. We'll take it one step at a time. Sorry. And then, remember, you're solving for what? You're solving for, yeah. So we're going to divide by 4x. Yeah, we want the h to be by itself, so that's the only thing we're not going to move, right? We're going to move everything else. Everybody good with that being the H value? So now we can take this and rewrite the volume equation so that it is purely in terms of X. Are we okay so far?
Like related rate, like,
Yeah, well, I think related rates, we did have, the cone problem where we got to make that substitution. Yeah, but I guess in that sense, it is, we are basically getting our, equation down to one variable, so we can find the derivative, but here, there's no time involvement. There's no dx dt or dv dt. Everything is, it's just v prime. We're just gonna set the derivative equal to 0. All right, so this looks a little messy. We don't want to find the derivative at this point, because if we do, we got to go through product, chain, and product, chain, and quotient. This is too much. But this is easy enough for us to just clean up and just rely on power rule, because there's only one term in the denominator. So let's see if we can do this. See if we can distribute the x squared through, clean it up, separate into individual fractions, and then clean up every single term. This should just feel like two separate terms that we can find the derivative using power rule. Okay, so we can try that. I will walk through this then. Okay, so I got 27x minus x cubed over 4. I'm basically ready for power rule. How can I rewrite this so it doesn't look like a quotient rule problem? I don't have to go through quotient rule for this. Okay. All right, much easier, right? These are the same things, but we would much prefer to find a derivative at this stage than this stage. You can find a derivative here, but it's, why make things difficult when we can just do it once we can clean up and do it from here. Okay. So that's, so basically that's it. This is the hardest part is to get to this stage. Now you just find the derivative, set the derivative equal to 0, find critical point, and then that is going to serve as your dimension for your optimal solution.
27.
I did 108 divided by 4. I used my calculator here.
What do you want to do?
Well, we want to get it ready for power rule so that we can find the derivative. But we prefer to not go through quotient rule here, so we want to clean up all the ways to see if we can just rely on power rule. Okay. 27x becomes minus what? 3/4 x squared. Okay, and we're just always going to set the derivative equal to what? Yeah, you're just finding critical point. So really, if you want to sum optimization down into a few words, you're just finding critical points. That's really all it is. But it just feels complicated because you have to go through all this. You got to jump through all these hoops to get it down to this equation to find those critical points. Okay, dividing by 3/4 is the same thing as doing what on the other side? Yeah, multiply by 4/3. And use your calculator here. I get 27 divided by 3 is 9. 9 times 4 is 36. X squared equals 36. So x, the length of our base, must be equal to what? 6. Now, algebraically, we're going to get what? Plus or minus, but obviously -6 is not going to make sense within our problem. So, but yeah, technically plus or minus will show up, but only 6 will make sense. So this is telling us that if the base is 6, it will fulfill the condition of it being 108 square inches, but we can still maximize the volume. But yeah, basically a square base. Anything that is closest to the square or a cube will optimize the space inside inside your container, given the restricted amount of material you can use. Now, whenever you solve for x, you basically are at the answer stage. You just have to figure out what the problem is asking for. Is it asking for the dimension? Is it asking for the height? Is it asking for the optimal volume? So when you solve for x, you've earned the majority of the points, but just make sure you go back and read the problem and see, are you giving exactly what they want? Okay. So here this says, what dimensions will produce a box of maximum volume? It's not asking for the maximum volume, it's asking for the dimensions. So dimensions is just the length, width, and height. Well, I know my length and width, which is 6 inches. How can I find the height of this box? Yeah, let's plug it into whatever. We have all these different equations. So when you plug in, you're never creating a new equation. You're just relying on one of the equations you've already built, and you're just plugging in. Okay, so once you get to the stage, it should feel easy. You're just gathering information that the problem is asking for. Okay, so so don't think like I gotta create a height equation. You already have an equation available for you to use. Okay, so height is 108 minus x squared over 4x. Plug that in. I got 3. Did you guys get 3? Okay, so the dimensions are 6 by 6 by 3 inches.
Always looks like the same.
Right, because we already know it's a square base.
Yes.
So we have one of the bases, we have the other one. Okay, next page.
You only put the inches at the end of the
Yeah, I did. I tried to do that here, inches. What are we asking about?
You don't say like 6 inches times 6 inches times 3 inches. You just say 6 times 6.
Yeah, you can do that. I just did a shortcut, but. Okay. All right, next page. Similar idea here. It's just that now it says renter has 200 feet of fencing to enclose 2 rectangular spaces. What dimensions should be used so that the enclosed area will be a maximum? So here we're trying to optimize what? Area. Yep. You see that word maximum is describing area. That's the equation that you want to find the derivative for. So you can put a star next to area. Now, what's the area of my region here? Yeah, is it x squared or is it two x? Two x, right? It's length times width, so the whole length here is x plus x, which is two x. So two x times y. Okay, now, what do we need to do before we find the derivative? Yeah, we want to get this down to what? Just one variable, right? So we need help. We need help from a different equation. We have 200 feet of fencing. Anyone know which equation or what is that referring to? Yeah, that's a perimeter. Right, so perimeter is just adding up all the sides, and if we add up all the sides, it represents how much fencing we have. So the perimeter is, what are all the, if we add up all the fences, what is that in variable form? Yeah, 4x plus 3y, good. So we have four fences that are horizontally facing, and then we have three that are vertical, or in this case, I call it vertical, but just from our perspective. Okay, we also know how much fencing we have, so that's 200 feet. And now we have to find a way to get this one of these variables to go away, and with the help of this. Now, is it obvious? Is there an obvious, easier variable to solve for, or are they about the same? About the same. So because they're about the same, my tendency is I like to solve in terms of x. That's just my preference, but I'm just going to replace y. If I replace y, then I can find the derivative in terms of x. It's no big deal. If you want to flip it around, you'll get a different answer initially, but once you get all the dimensions, it'll be the same. So I'm going to target the y variable to replace. So I need to find a replacement for y. So I'm going to solve for y here. Okay, how can I solve for y with this equation? So I can put that in here. Okay, good. Right, 4x. And then we can divide. Everybody comfortable with that process of algebraically moving things around to get it to the variable that we want to use?
But why do we like find the y variance of the x?
Because I want to find a replacement for y in terms of x, so that when I make a substitution, if I replace y in terms of x, then I'm able to find the derivative because I have a much easier time with the derivative if I just can get it down to one variable.
Yeah, for x, to find a replacement.
For y, it will work the same way.
Which one would be harder?
Not necessarily. This one, it doesn't feel like it's harder, right? It'll be 200 minus 3x, sorry, 3y over 3, which is the same. Yeah. Numbers are a little different, but the process won't feel any more difficult. Okay, so again, we're going to try to do what before we find the derivative? Simplify, right? We should just be able to rely on what to get to the derivative? Power rule, right? There's no need for anything more complicated. There's only one term in the denominator, and it's not even a variable, so we should be able to get it all nice and clean, where the derivative is going to feel very
You don't
manageable.
have to like push rule.
Right, yeah. So with optimization problems, the problems I give you, it's just power rule, right? Just have to get it down to something that you can rely on power rule for. Okay. Split up into individual fractions, push the coefficients out in front. Is everything nice and clean, ready for power rule? Yep, A prime. What's the derivative of 400 over 3 times x?
4 over 3.
Yeah, just the coefficient. Good, yep. set equal to 0. Dividing by 16/3, same thing as multiplying by the reciprocal. These cancel out. X is 25. Yeah, there you go. Same. Mhm. Yes.
Why don't you do like the faster? X over 3x.
What do you mean 5/3?
Like, you don't have to put the 2 in front and then,
Subtract 1 from the exponent?
yeah,
Yeah, so the exponent is just 2, right? So what's 2 minus 1? Just 1, right? So I want to do something more complicated. It was like x raised to the 5/3 or x raised to. If it's x raised to a integer value, then the derivative should feel a little easier.
Just put them all in.
Well, let's see. What I solved for x, so now it should get easier.
No, you solve for y.
Huh?
You solve for y now, right?
Right, because why? What does the problem say? It's asking for the dimensions, yeah. So they just want x and y. So if we have x, then we can plug in and solve for y, right? Yeah. Again, once you solve for x, you're never having to recreate a new equation. Everything that you need is going to be already above you, so just have to look for it. So my dimensions. 25 feet by 100 over 3 feet.
Wait, so where the dimensions in there, I want to. You need to write it out that way, right? Like, for the-
Yeah, yeah. All right, circle number 2, this is what your problem will look like here on the test. Very similar to this one here. Now, this one has a little more involvement. We are still dealing with volume and surface area, but let me read the problem here. It says this rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of a space is twice its width. Material for the base costs $10 per square meter. Material for the size costs $6 per square meter. Find the cost of material for the cheapest container. Hint, you're trying to minimize your surface area. We're trying to find the optimal cost. We're not paying for the space inside the box. We're paying for the material that makes up the outside of the box. So that is how we know that we're optimizing the surface area. We're trying to minimize the cost. So cost is associated with surface area because we're not paying for the volume, we're paying for the surface area. So I'm going to use spaces for 1 and 3 to do this problem. We're going to see 1 and 3 here. So here's my drawing the box very well here. So I know that, the length of my base is twice its width, so I know that my base is gonna be two x and x, right? I know that's gonna be the relationship. There's no relationship with the height, so I know it's gonna be some unknown, variable in relation to x. There's no connection between the base and the height, so I'm gonna use a different variable for that. Right. We know we have to involve volume. So what's the volume of this box? Yeah, which is two x squared h. Let's build the surface area. So we'll build the surface area first, and then we'll bring in the cost. All right, so let's do one set at a time here. What's the base of the, or what's the area of the base? And what's the area of the side involving two x? XH. And do we have another one? Two of them, good. There's one in the front, one in the back, right? And they're both the same area. Good, and there's two XHs because the shorter vertical side, or the smaller side has XH, and there's another XH up here. Yeah, well, do we have another two x squared? Why? It's an open top, Question? So two x squared is for the base. 2xh is for the larger vertical side. Another 2xh is another vertical side, and then xh, yeah.
Can you combine all the XH?
Yes, we are. I just want to kind of separate them for now so that we can see where all these are coming from, because if you know the area of a rectangle, you should be able to create your surface area. There's no need for me to give you a formula for a surface area equation, because you're just adding the area of the surfaces, right? So there's no, if you know that, you can be able to build it. Now, surface area has cost associated with it. All right, so we're gonna turn this into a cost equation in a second, because how much is associated with the base? What does the problem say? Material for the base costs $10 per square meter. So we have to make sure we multiply $10 with that amount of material that we're going to be using. Material for the sides costs $6 per square meters. You gotta do what? Multiply this whole thing by 6. So we're going to transform the surface area into a cost equation. What does this become? Good. Yeah, so this is 4. Sorry, this is not divided by, I gotta multiply this whole thing by 6. So this is 4xh plus 1xh plus 1xh. So this whole thing is 6xh, and I need to multiply this by 30, sorry, by $6, right? So that's how we got that 36xh. All right, this is the part that students struggle with here. Are we good with building that surface area equation, involving the cost, and then turning it into a nice cost equation?
Well, I feel like it's open top.
It depends on the problem. Sometimes if I say closed top, yeah, so how would this be different if this was a closed top?
We got
Another 2x squared, and this will be 4x squared times 10 will be 40x squared.
like, but you think on the test will be open top?
I'll specify it. Yeah, so you're not gonna have to guess. It'll be one or the other. All right, find the cost of the material for the cheapest container. So we know we're gonna optimize cost. We need help with the volume. We need help from the volume equation, right? Because this H is kind of sticking out we want to replace that H. So we have volume, how much, what's the volume of our container? 10. So 10 is equal to 2x squared H. So we're working with the supporting equation to help us get that cost equation down to one variable. So what can I do to get H by itself? Divide by 2x squared, right? Okay, can I clean this up a little bit more before I insert it into the equation? 5. Close, it's not 5x squared. 5 over x squared, right? 10 over 2 is 5, but the x squared is going to stay below. It's not going to move up. So I'm going to substitute this piece into here so that we can get this down to one variable, so that we can find the derivative and then find a critical point. Okay. Okay, there's my cost equation. I just want to rely on power rule. So what can I do to clean this up so I can rely on power rule? Yeah, multiply and clean this up, right? So 36 times 5. Almost there. Before we find the derivative, we should do what? Bring that up, okay? As what? Now it's all clean and ready, right? Down to one variable, no product, no quotient, no messy rules, just a nice clean power rule. Okay, so now we find C prime. What's the derivative? Minus -2. And then we set C prime equal to what? Always, yeah. So you just find a critical point. Just doing a little bit of cleanup so that when I solve for this algebraically, I'll prefer to work with positive exponents. It just feels more straightforward to me. Okay, so if I just put that 40x over 1, I can cross multiply and solve for x. Yeah.
When you multiply the 36 times the 5 over x squared, why wouldn't you multiply the x out with it? Like, why wouldn't it be like 180 x over 36x?
The reason why is because I'm multiplying 36x over 1 times 5 over x squared. So the numerator multiplies with the numerator, denominator goes with the denominator. Right, so when we distribute, we never distribute to the numerator and denominator. You only do that with exponents. If it's a coefficient in front, just the numerator. So if you can put a 1 down there to help remind you that it's the 1 that goes with x squared, not 36x. Okay, cross multiply. Take the cube root. Like 1.651. So we have the dimension for our box container that is the cheapest, based off of our restriction that it has to be 10 cubic meters. But it says, is it asking for the dimensions though? Cost. So I can just plug this 1.651 into what? Yeah. So I have multiple cost equations here. You can use this one, you can use this one. You don't want to use C prime, that's something else, right? So you just plug into one of the cost equations, and then whatever that gives you, that's your optimal cost. Yeah, second one or the first one, it's up to you. Yeah, maybe the first one, so we don't deal with negative exponents. Okay, so, so for homework, on page, 36, I'm just gonna have you do number 6 and 7. That's it. So I'll send out a reminder. So page 36, you're just doing number 6 and 7 for your homework. I will update, the website so that you guys can see those problems. I won't be able to check until Wednesday, but it's your homework. So tomorrow when you come in, I will have, packet, and I'll have Ms. Love go over 2 curve sketching problems with you, and then an optimization problem involving the box, so you know what to do. All right, get your votes. You can go. Okay, you can go tomorrow. I'll be here. I'm just using the day to catch up on the reading. But I will have help desk tomorrow morning as well. We'd be like for one thing. Yeah. From the last time. I'm just gonna be down the hall. Guys, help sessions tomorrow morning, afternoon, Wednesday morning, Wednesday afternoon, Thursday morning, and Friday morning. Okay, so I'll send out that help session schedule tomorrow. I wasn't here. The bill's in New York. There is not like the old days. One of the finally started getting. We came back to the win. Yeah.
Administrator like email the text itself.
No, we didn't have time, we left too much time.
Oh, got it, too much time.
But like,
It was big, it was accident. Then like, sorry, we didn't get to set it all.
You're taking Monday, or school, you're taking class.
we lost.
I still love
I'm just saying that because in case nothing else works, you just go to class. Like before school, class.
Well, it's crazy.
Yeah, yeah.
We're taking again.
You got it, that's fair, thanks.